So today's session is an idea that just occurred to me in the last week as I was leading the session for YakCon. So we did 2 Sunday sessions on distributed systems and robotics. So the robotics part is, of course, from this group, and the distributed systems part is from the discussions we've been having on the Monday track of discussions. So we did a combined track, and what I'll do is I'll quickly review what we did in the 2 sessions, and then I want to have a discussion, which is on that Rome page that I've linked. So let me explain what we did in the session first. So for YakCon, the first Sunday we played this thing called a pebble game, and let me pull that up here. It'll be easiest to explain through the spreadsheet. Can you guys see my spreadsheet? Can you see my spreadsheet? Just want to make sure my tab switching is happening. Okay. All right. So the idea behind this distributed rover memory game is from this classic paper I mentioned before on the power of the compass. And this is where the major result on the idea of pebble automata was discovered. So pebble automata is basically a very simple stateless robot that wanders around a grid, and its only form of memory is dropping pebbles or picking them up. And this major result was that all you need is 2 pebbles to navigate a maze completely, which is, by navigate, they mean visit every cell, which is kind of like a basic capability on top of which you can do things like navigation and more complicated things. Like if you can visit every cell with just 2 pebbles, that's kind of like a basic computational property. So this paper by Blumen first, 1967, I think, is kind of 1978, sorry, is the inspiration. Look at the game. Let's see. Let's look at this map first. Let me maximize this. So imagine this is your world. The black parts are obstacles, and the A4 and B5 are positions of 2 rovers, and they move 1 cell at a time, northeast, west, or south. And the number after the A or B is the number of pebbles they still hold in their cargo compartment. And the other cells with numbers are the pebbles they've dropped. So the A4 is each robot starts with 5 pebbles. So the A robot has started on the cell just to the east and has moved west after dropping 1 pebble. So that's how you read this. Whereas up there, the X means it has that cell has just been visited, but no pebble has been dropped. So the B robot started over there and moved right 1 step and did not drop a pebble. So the idea is, can you define a rule that allows these guys to wander around the map that is only dependent on detecting the number of pebbles that are in the cell and picking up some or dropping some? And as you can probably work out, this is extremely simple, but it's basically spatial computing. So you can define the behavior of an entire robot using a matrix like this. So the rows are, let's see, the condition of the northeast, west, south state of the map. So for example, 0, 0, 0, 0 means all 4 directions are clear, whereas let's say 1, 0, 1, 0 means north and east are blocked by an obstacle, but south and west are not. So that's how you read the rows. It tells you the accessibility state of the neighborhood. And then the columns are how many pebbles you detect on each, on the particular cell. So for example, you can say that suppose you are in this cell, it means 3 of the 4 directions are blocked, and your rule says I'm going to move south after dropping 1 pebble. So that might be a rule for that condition. So as you can see, this is kind of a weird way to define a state machine, and you can like map it to other things like abstract graph traversal. But this is basically a way of like mapping robotic movement in a distributed environment to computing. So the game was set up like this. So the game is to visit every open cell using 2 rovers as efficiently as possible. They cannot detect their XY position, so they don't have GPS. All they know is which direction is north. So they know which way they're facing and which direction is north. So they know their orientation and have a compass. and they cannot communicate except by like detecting pebbles. The pebbles are the only form of memory. The pebbles of different rovers are indistinguishable. Each rover can hold at most 5 pebbles, and any number of pebbles can be dropped or picked up. Of course, limited by number of pebbles already there. Let's see. So that's the game. And what I had people do was just try and get some intuition for how the system behaves. So like an intuition pump activity, and come up with like their own rules. So people came up with different rules and tried to like simulate them on paper a little bit, came up with some insights. And I was asking people a few prompt questions, which is what rule are you using? So an example of a rule is Laura was trying to go straight and spiral inwards in a left-handed direction. That's an example of a rule you might be able to implement. And I asked them, if you could get one bit of extra information, what would you pick? So a popular one was, where did I come from? So one way to implement that might be either a one-step memory, or you can have like a camera that is able to look behind, or like, in all 4 directions. So you can kind of like think of like a lot of state and memory information in terms of like sensor capabilities. So right now you only have a sensor that detects the number of pebbles in your current cell, but you can imagine, for example, adding 4 more cameras that can detect the states of the 4 cells you might be going to, right? So the whole point of this setup is to like transform your intuitions on memory and processing into intuitions on space and movement. So think of this almost like in a regular computer, you have a complicated like processing unit that accesses a disk via like a very dumb disk access mechanism, right? A read-write head. Now imagine that the disk is the entire world and the computer is just a read-write head, which can do very few simple things, right? So it's that kind of like a refactoring of what computation is. So this was the first activity. Let me go back to this here. This was the Pebble game. And then, of course, asynchronous week, I posted a bunch of readings. But the second session, I had people pick one of these readings to read. Most people picked the first one on Hobo Sign Language, but there's a short story I wrote on like what a very futuristic sci-fi map might look like. And there's this video talk on spatial memory, sort of the culture of how you do memory in physical environments. But let me just click this one open because it's kind of relevant. So you can think of markings you can leave in the environment as more complicated forms of indistinguishable pebbles. So indistinguishable pebbles that you can drop and pick up are kind of the limit of the least information bit-like artifacts that you put in the environment. And picking up and dropping is sort of the least invasive way of marking the environment. And you can think of like more complex things, right? You can carry a piece of chalk and mark the environment with chalk marks, which is kind of what hobos do. You can think of like more destructive changes to the environment. Like, if you're in a wooded environment, you can break branches. You can think of like the tracks, like Curiosity leaves tracks on Mars, and the tire tracks of Curiosity actually encode in Morse code the phrase JPL. So it's kind of like just a little bit of an Easter egg, but that gives you some idea of like possibilities where even your tire tracks can be a way of marking the environment. So this is kind of the basic setup. And in the second session, we had like an open discussion on, so you can look at this later, but like, what are your general thoughts on real world distributed memory for robots? And also the prompt was, what kind of mark would you invent? Like if you could do something like a Hobo Sign Language, but you want a language that's intelligible to both humans and robots, what would you use? So basically an environmentally mediated map of, not a map, environmentally mediated sort of way of being situated in the environment and using it for both communication and memory. So that's the basic idea. So these are the 2 exercises. So lots of good discussion. Okay, what I wanted to do for today is kind of bootstrap maybe a discussion in our regular group here based on what we did here. So let me do. Any questions so far on the activity that inspired today's session? Is it clear what I was having them do and what we did?
Tell us how it actually worked out? Are people able to deal with it, you know?
The Pebble Automata game, I think, yeah, it would have taken more time and it would have been ideally better done as, say, a little JavaScript widget on a web page, because simulating it either on paper, as one person tried to do, or on a spreadsheet was a little too mechanical and hard. But this, I actually started trying to write it up as code, but I didn't get very far. I was trying to do it in MATLAB. But yeah, you can imagine where, let's see, if you could, where's my thing? The spreadsheet, if you had like a JavaScript page where you had, let's see, this kind of basic grid that you could define by just like, zeros or ones or something, and you could specify this rule matrix for how your Pebble automaton ought to behave. This would have been a much more powerful way of like getting people to explore their intuition. But despite that, I think people got some basic ideas. Like I thought the ideas of like spiraling inwards, using the pebbles as sort of a quick memory of like which way to turn. So maybe one pebble means last time you visited, you went north. So then you sort of rotate clockwise 90 degrees and then go east and add a pebble. Then two pebbles means you rotate further clockwise, and you can kind of do fairly complicated logic, and people were starting to get that. The second session, it kind of like expanded into a general discussion of like memory systems. Mayor, you mentioned song lines, which is like people remembering paths and like walking around in the desert. Like, how do you remember a path using a song? So there's like more things than just marking the environment. You can like remember a song. You can sort of come up with a language where you can say things to other agents you meet on the road to like communicate trail information, which is an example I came up with. So you can sort of generalize this idea of like taking memory and communication and putting it out there in the environment you're sharing, as opposed to like something that's mainly inside you. All right, so let's have a more structured discussion about this, which is this thing that I wanted to do. All right, so the basic idea, of course, you must have recognized is you take the
second,
yeah.
Venkatesh, could you say a little bit more about wave, I should say, swell navigation of the Polynesians in this context? That's
Yes,
even more interesting than song lines.
Yeah, so the example I came up with for terra marking is actually terra marking on water. So water is a very difficult environment to mark, since you can't like drop pebbles or otherwise leave markers. Like you can have buoys and things like that, but it's fundamentally a tougher environment. But I was thinking of Polynesian wave navigation. I have a book on that. It's like a fascinating subject, maybe just behind me somewhere. But yeah, the way the Polynesians do wave navigation is they have like oral culture about how wave patterns feel between islands, because the islands are like they kind of like refract waves and reflect them. So based on like how you feel the waves under your boat, you can actually do position location. Let me see if I can quickly Google up an example of a wave map.
I think from what I looked up, waves change, but the direction of the swells stays the same.
Something like that, yeah, depending on the seasons to some extent. But yeah, I think part of the reason they do it is that it's robust to bad weather in some ways. Like if you have overcast skies and can't look at the skies for star navigation, the waves are still there. But this is what wave maps look like. So these sticks apparently show you the directions of swells, and experienced wave navigators are able to kind of lie in canoes with their stomachs down and feel it through their stomach, apparently. And I learned about this, by the way, on a Hawaii vacation where our hotel room had one of these things on the wall. And I was like, what the hell is this? And then I looked it up, and these are basically maps of the ocean. So another way of kind of like terra marking, though this is kind of like not marking the territory itself, but making a map of waves. But you could say that you're storing information about navigation in the environment itself. So you're kind of like feeling the waves and that's a way of like reading the ocean like it's a hard disk, right? And then of course you, with your memory artifact, you recognize the significance of that. Like, if there's two wave fronts coming to your stomach, you recognize that maybe you're south of this particular island or something like that. So it's one of my like long-term projects to actually understand how this works. Okay, yeah, so those are some examples of like basically externalizing both computation and memory into the environment and keeping the agents much, much simpler. So that's the discussion I wanted to have today. So what I want to do is very quickly make a basic comparison of two types of computing and then have these discussion questions that maybe we can talk about. So the discussion questions I just want to queue up is, what's a good design for a terramarking computer that works by these principles? Can we do things like augmenting the physical environment? Like, of course, pebbles on the ground is an extremely low capacity memory. It's like, a few bits per square inch or something, but you don't have to be limited to that in a practical situation. You can do things like, I know like spies, I don't know if they really do this, but there are cases of like people putting USB flash drives in walls and things like that. So it's like, for scavenger hunts. So you can go and there's a USB drive that's embedded in the wall with concrete, so you can't actually take it away, but you can like plug it into your computer and read what's on that drive. So you can like think of like more sophisticated ways of doing enhanced environment plus plus type memory and processing. You can even do things like, you have a very simple robot that's wandering around that has maybe an Arduino level processing capability, but occasionally it needs like, complex GPU capability, and it goes somewhere where there's like a GPU just sitting there and it plugs itself into the wall, uses the GPU for a while, and unplugs and goes away. Looks like Joshua dropped. Or is he still there? He just turned off his camera. Okay. Oh, you're still there. Okay. All right. So that's kind of what I want to talk about. So let's. I just made two lists comparing traditional computing to what I'm calling embodied and situated computing, which I think is how the robotics community also talks about it. I know there was some work in the 90s about situated computing and situated automata, but point by point comparison. I'll just go through them side by side. So traditional computing, it's basically built around powerful, disembodied, static, and highly stateful agents, namely computers. Whereas situated computing, I think the default should be embodied, mobile, limited capacity agents. And in the limit, you ideally want stateless and memoryless agents because they're like super robust and like reliable. In traditional computing, there's no meaningful notion of embedding or containing space. So a computer doesn't really know its X, Y position until you like attach GPS and tell it. It doesn't really know what time it is with reference to, the stars or the waves or anything unless you give it a clock signal or a time protocol. Whereas embodied computing exists in a shared open space-time, and that contains most of the intelligence, including location and timing information. Like if you're a robot out there, you don't need an explicit clock. You can just look around and notice that the sun rises every day, and you have a clock signal right there. There is an explicit network for interconnecting in space for traditional computers, whereas for embodied computing, the agents kind of just live in the same space, so they're implicitly connected. Same thing, memory is a way of interconnecting in time, right? I save a piece of data on disk, and a day later, future me can read that. So it's interconnecting with myself across time. And again, I would say this is sort of implicit, and space and time are kind of converged in situated computing. Permissioning is kind of interesting. Let's see. So I'll actually read this one first. So in situated computing, I think the default is public until made private. So for example, you have a notion of co-location, so things collide and you can only get so close to each other. Whereas in traditional computing, co-location is kind of almost a constructed notion, like, namespace or address space collisions are kind of what maps to co-location. in distributed situated computing, you have mutual visibility. So cars on the road, you can actually just see other cars around. You can see whether they're driving dangerously. You can learn a lot just by looking at another agent in a shared space. Whereas in general, I would say in traditional computing, things are default invisible unless they're made visible via discoverability or hostile actions like sniffing. In general, you're kind of like isolated in even the limited shared space. So the natural laws of things like line of sight visibility are kind of not that relevant in traditional computing. Let's see, item number 6. I think it's fair to say all dynamics in traditional computing happens in the private random access memory of agents, whereas in situated computing, it happens via modification of the environment. And it's a shared environment, number one, and also whether it's serial or parallel or random access is actually a function of the mobility. So I would say like most typical robots wandering around in an environment, they're kind of like not exactly serial, but they're not random access either. So our Pebble automaton example, it can wander northeast, west, south. So it's not exactly sequential access like a disk. A disk is basically one-dimensional memory that's arranged as a spiral. But this is two-dimensional memory with 1 degree of freedom in how you sequentially wander it. So yeah, it's not private random access memory. It's public serial plus memory is the default, I would say. Traditional computing communication is kind of default direct, or I should probably say explicit, where you explicitly form an intention to communicate and then you send a message to another agent who you know exists in a shared address space and whose address you know, something like that. And even things like hacking and intrusion kind of fit within the paradigm of private only spaces connected by like an addressable space, where if you hack another computer, it means you're like accessing it via its published network address and you're hacking it via that address. Whereas in distributed computing, it's like, you can watch another robot. If it's flashing lights, you can kind of like infer certain things from the flashing lights. Let's see. So persistence is memory operations for one agent. So item number 8, whereas persistence in situated computing is a property of the shared environment. And I think fundamentally, situated computing is more software 2.0 in Andrei Karpathy's sense, whereas in traditional computing, it really is more software 1.0, where code is more powerful than data. I would say distributed computing is unnatural for traditional computers. So you can have things like shared memory, and then you have a messy memory hierarchy. But processing is still fundamentally in cores and threads in traditional paradigms. And then you need the abstraction of the network to meaningfully tie the distributed computing together. As I would say, in situated computing, it's kind of like distribution is the natural state of affairs. So memory is shared by default and naturally managed. So you move a pebble and walk away, another robot can come and do something else to the pebbles, right? So you actually have to construct privacy as an explicit act as opposed to being the default. You have to construct borders and say the other robot can't come in here. And processing is an emergent property of the environment state. So there's no real equivalent of like a core that owns a problem and has a processing thread on that problem. That's not the right way to think of it. It's more like, I think of it more like these Pebble automata wandering around a shared space. It's kind of more like if you think of the Unix shell environment and things like, simple commands that can be piped to each other. It's really a little bit of that, but an enhanced version of that. So one automaton wandering around might do something like, anytime I see 2 pebbles, I pick one up, whereas another automaton is walking around with the rule, anytime I see 1 pebble, I put an extra pebble down, right? So what's the emergent processing behavior of that system? I think of it as a Unix shell where the commands are wandering around as opposed to you are invoking the command. Something like that is what's happening. So I don't know if that made sense, but it's something like that is happening. And you don't need an abstraction of the network for all this to happen. It's kind of like just natural laws that's making all this happen. Let's see. Close up this part. All right, final 2 points. I would say traditional computing is private by default, social by design, whereas it's the reverse in situated computing. And the biggest one, which I've kind of like not philosophically really kind of come to terms with, is it feels to me that traditional computing has this notion of agents being these detached observers that are outside the compute environment proper. So you've got the network and the memory as the equivalent of the commons, but the actual computers are outside that space. They're operating on it, but are outside of it. And in situated computing, it's like the computing agents are actually part of the environment of other agents. So for example, if there are two robots wandering around, one robot can actually put a chalk mark on the other robot. So kind of treat it as like an indistinguishable part of the converged environment. So I don't know quite what to make of this this whole notion of these computers are part of their environment. But it was just a thought that occurred to me. All right, so what are the implications? I think some of the implications, if you want to work with the situated computing paradigm, is build the simplest possible robots and treat the environment as the primary comms and memory medium. And anything else is kind of like a plus feature. So if in addition you have like a TCP/IP network connecting the robots, that's a plus network. It's not the primary. The primary is the fact that they share space. Same thing with memory. If you have a shared hard disk or a network file server, or like you can access each other's hard drives, that's kind of a plus version of it. The primary way you have memory is in a shared space and time that you can modify by marking it, right? And you kind of treat all behavior as environment modification. So we're used to thinking of robots as moving in a space and kind of manipulating the space in limited ways. But maybe you can think of it as robots existing at all is a kind of like computation. So you take the, national park motto of leave only footprints and take only pictures, and say this is kind of the opposite of that. The footprints are the baseline of how you mark the environment kind of naturally by just existing in it. But yeah, footprints can leave bits of information in the environment for others to act on. And it can be conscious, like the tire marking example of the Curiosity rover, right? Footprints don't just have to be unintentional information that Sherlock Holmes reads and like infers who did the murder from. You can, for example, like literally, if you're walking around in a national park, you can kind of like carve your initials into the shoes of your into the soles of your shoes, so that wherever you're walking, you're leaving your initials behind, so that if you get lost, a search party can like follow your trail and distinguish your shoe prints from somebody else's shoe prints, for example. This question came up in the session where one of the constraints I imposed was you can't actually distinguish pebbles. And I think one of the participants said one of the extra bits of information they would like is make the pebbles distinguishable. So people have different colored, or robots have different colored pebbles that they drop. Okay, so that's my setup, and I want to leave it at that and open up the discussion questions. The link is in the Discord if anybody wants to continue looking at these points. But yeah, so what do you guys think?
I have various thoughts, but before I go there, how does this connect to the memory model you gave yesterday at the governance channel, distributed governance, which talked about what's really processing memory? So if you have, like in the brain, you have columns and they're connected laterally and horizontally. So this memory, which is distributed, is not just memory, it's not just processing power, it's memory that does something. It's as if when you play hopscotch. So when you land on the number 3, you have to hop on one leg.
Yes.
Okay. So that's the kind of memory that I didn't notice you talking about, but that makes you more, the response, the environment is more controlling of your behavior. You don't?
Yeah, So I didn't mention that point. So for the rest of you, in case you're confused, so yesterday's distributed systems call on so Monday morning, we read this
Yeah.
paper on Numenta's cortical columns based AI model. So Numenta is this company founded by Jeff Hawkins, who founded Palm Pilot, and then he went to found a neuroscience company that does research. And he's been really into this notion of cortical columns. So the human brain is organized as cortical columns, and it seems to be weirdly more spatial than people normally assume. So quite literally, if you're looking at a visual field, or if you are touching something with like 5 fingers, like the example in the paper is you've got a coffee mug and you're touching it with 5 fingers, and each of those fingers actually maps to like a cortical column in the brain. And because so each fingertip, for example, might um, guess that you're touching a coffee mug, and then the future of how it moves around the coffee mug and grasps it is driven by the prediction that it's holding a coffee mug, and it's going to expect certain things as the fingers move, right? So vision is the same way. So apparently the brain organizes its memory in sort of like an environment spatial mapping way in a very literal sense, and processing is organized in that spatially linked way. And as you learn more about the environment, the memory kind of like gets laid down in that spatially distributed way. And I think the more you go into this paradigm, the more processing memory and storage memory. So memory as storage, the metaphor of memory as storage starts to break down, and memory becomes like a converged notion of both storage and processing together. So if you leave a pebble in a cell and say, that's not just sort of bit of information, it's also an instruction that if I see one pebble in a cell, I have to turn eastwards. It's a processing instruction that's laid down in that cell, right? So in a sense, you've like basically conflated data memory and processing memory. So it's like the L1 cache is both at once. So that's the point Amir is getting at. So I think that becomes, I guess, a kind of design principle which I should capture here. So an implication is code memory and data memory converge. Something like that is what's going on.
Yeah, let me give you a somewhat different example. For handicapped people, depending on where they position their wheelchair, either a different action will happen or the remote that they have will do something else. If they stand in front of the TV and they, press on the big red button, the TV will go on. If they stand in front of the refrigerator and press the same button, the refrigerator will open. So the processing can really be location dependent. And before that, I gave the example of hopscotch, which is the opposite. When you go somewhere, you got to do something. So that's just a thought. When you were talking about it, I was connecting it to yesterday. But I have another example, but you asked 2 prompts. So one of the questions you talked about is how do we embed memory? And the answer is, of course, to me, wireless. I mean, you're not going to plug in. You're going to go by and you're going to have a wireless Bluetooth connection. But the example of a terror marking robot is an ant. Okay? An ant is a very simple robot. Yes, they work in a swarm, but they leave a pheromone trail behind them wherever they go. And that is, exactly terror marking.
Yep.
So one last thought that I had, one is from the real world and one is from fiction. So from the real world, you see English gardens from the 18th and 19th century, and they have ruined statues and so on. So in that garden design, the idea was that different parts of the garden would put you in a different mood, and you would have different pathways you're supposed to walk through the garden. So walking through the garden, let's say, programs you. Okay, now you should be thinking about history. Now you should be thinking about hope. Now you should be calm. And related to that in fiction, in the Amber series of Roger Zelazny, you have the pattern, which when you walk the pattern, things happen to you. You get capability, you get memory, you get whatever. So I'm just saying when we talk about position, there's also order that we have to think about.
Yeah, and I think lots of game mechanics have that kind of logic where if you do certain things in a certain sequence, you will undergo certain state changes, as in like acquire powers and stuff. So this is something, yeah, I think I didn't put in
So
my principles here. You can make the robots themselves evolve and change as a function of their history of wandering in the environment, right?
so I was gonna flip it, when we talk about virtual marking, what if each website my virtual rover goes to, it goes to the Art Collective website or it goes to CNN website, that is also a terror which it can mark and which can affect it. And in the extreme case, you can imagine a deep learning model with different parts of the model or different weights happen depending on where it is. I don't mean that it recognizes where it is. I mean that if it goes to one place, so, 1/4 of the memory bank goes off and it goes to another place, so all of these weights, double in strength. So this whole convergence of spatial, either in the weird world or in, cyber world, and behavior, it has other possibilities.
Yeah, so terra marking, that's a good point. There are other terras, like apart from, of course, other planets, you can think of like lots of other things as conceptually being spaces. Yeah, more thoughts?
I have one. So I don't know if anyone here visited Dynamic Land when it was like open, but that was sort of the first time that I directly experienced like programming in a situated environment, right? So the idea was that they had cameras and projectors pointed at a surface like a table or a wall, and then you could put pieces of paper down that had a pattern on them, and it would recognize, like it would run the code on that paper, but it would also, as like a primitive of the environment, like you'd be able to know where your paper was in that environment. Like, so your code, like part of its properties would be like, oh, I'm like here relative to the table's coordinate system. And you could see things like where other entities on the table were. And so to me, that was like a very, I don't know, like different feeling of programming where it was in, the code itself was embodied. And so you started to think about like, oh, okay, like I can change my properties if I'm close to other things, or I can send out, like the whole thing was kind of based on requesting. Like you would sort of make I forgot what they called them, but like you'd sort of make statements and then you like make requests. And so like other things could honor those requests or use your statements if they wanted to, right? So it's that similar kind of permission. Like it's not it's public by default, but like because of that, you kind of don't just do whatever. You don't take everything as like true or good for you by default.
Is this? I remember watching one talk on dynamic land, and I saw some videos of how it worked. But uh, this thing you're mentioning about like you can make statements and others can use it, something like that. It sounds like a more open version of the ROS pub sub type mechanism. Is it a is that a good way to think about it?
I think so. Yeah, like I haven't really gotten deep into ROS, so I'm not 100% sure, but Yeah, like the idea was that you had these entity, like the other weird property was as like the environment was running all the code that it saw, but like as individuals, you could take a piece of paper and put it on the table and it would start running that. And so like anybody could kind of walk over, and the nice thing about that was that you could also talk to the person like running the code that's maybe like taking over the whole table or spamming or something, right? But
this makes me think that there's sort of 2x2 here. One axis is how open the environment is that you're situated in. So one extreme is a traditional computer that's just a box that doesn't even know it exists in time and space, and the other extreme is just a wilderness. And dynamic land seems somewhere in the middle. It's an extensive space that has like natural notions of time and space, but it's designed and contained, and the container itself is kind of like a sophisticated computer. It's not a wilderness. And I guess the other axis would be something like, okay, what are the two axes I was thinking of? Open versus closed, and designed versus natural, I think is what I'm thinking of. Where I can't think of like closed and wilderness, but maybe something like, I don't know, public computer with a lot of viruses or something like that. But I'm trying to think of like, how can you extend the logic of dynamic land to a wilderness? Like there's rocks and birds and stuff doing random shit there. So it's not in that sense usable the way dynamic land was. But yeah, this is definitely in somewhere in this discussion. It belongs in this discussion, the dynamic land type model.
yeah, it's more of the virtual world, I guess, right? Like yeah.
I think the one it's very science fictiony, and I like the idea of like pushing computing in this direction. And I also think it's more natural for distributed AI type computing. But the one thing that I think it's really weak at is intensity of capabilities. So by that I mean like a modern high-end CPU packs like a huge amount of computing power in like a couple of square centimeters. Same with high density modern memory. Like a very tiny amount of space contains like huge amounts of like memory, right? Whereas the natural environment, it's kind of very diffuse. And you can also say the same about networking. Like an optic fiber cable connecting two computers is like extremely high bandwidth. Whereas the natural environment, if you look at like the distribution of like compute, memory, and communication capabilities, it has like extremely low levels of all three things. So it's like almost cosmic background computing capabilities or something.
I think the right way to think about it is not bandwidth, but in latency. Like the reason that they're all close together is because the speed of light actually starts to matter. And so it's about the latency for all. So the physical environment is actually super high bandwidth. It's just really, really slow. Which actually brings me to the one thing I wanted to mention, was talking about traditional computing. If you were to try to apply some of these concepts to how traditional computers are networked together, you get kind of hilarious results. There's a hack. I don't know if you know what to ping another computer is to send a very specific crafted packet that other computer is supposed to just reply with, echo the same thing back to you. And so there are some hacks that folks have written that allow you to essentially use the network itself as a database or as a file system, building just on top of those packets. So you use it's the only true cloud, and it's not actually using someone else's computer. It's using the network substrate itself to store your data, but they're always in motion.
There's a fun backstory, I think, for the term ping is I think it came from submarines. Like I remember watching Hunt for Red October, and then I looked it up or something, and I think, yeah, the term was used in submarines first, which is kind of funny because they're like physical objects in a physical environment detecting each other in literal space. And now it becomes a metaphor for abstract address space, basically.
Yeah, it's like, what would a packet sound like?
this something just occurred to me, but oh, you said that you should not think of the physical environment as low bandwidth, but just high latency. But I think it also is low bandwidth in a specific sense, which is if you look at the information content of, say, a square centimeter of soil, there's actually a huge amount of information there. Like, there's billions of atoms and they contain lots and lots of information. But 99.999% of it is like wild random information, which maybe some microbes are using, and there's like stuff you can detect from the soil about like the last solar flare. So in a sense, there's like obfuscated natural information encoded in the environment. So I would say the way to think of the natural environment is it's high latency plus low availability, as in most of the capacity is used up by like wild content. And if you want like the low entropy available resources, it's actually very low. So if you think about, for example, the Pebble automaton I talked about, and you try to implement it in a regular environment, like say a forest, it would be pretty much impossible because a forest is like a messy, cluttered, not level thing. It does not have like grid markings on it. Whereas if you actually wanted to play the Pebble automaton game, you would either do it on like a software, like virtual screen, or if you wanted to do it physically, you would like clear away space, mark out a grid, make sure it's completely smooth, make sure the camera only detects a white background and the pebbles are very clearly marked on that background, and the pebbles are a particular shape that you can pick up. So in a way, what you're doing to make the environment suitable for computation is flattening everything that's not legibly part of your own computer, right? So you cannot directly apply the Pebble automaton model to a wild environment. You have to like civilize the environment before it's usable in that way.
Or you need lots of information redundancy to ensure errors don't crop up.
Right. Yeah. Yeah. I guess another prompt I had was, this is obviously kind of fun for toys and academic experiments and for learning distributed computing concepts. But is there like real world practical application where this kind of computing is actually the better fit than traditional computing? Like what real world application would you preferentially design by these principles as opposed to traditional?
Very small computers. In other words, having a CPU uses power and takes up space, and the smaller the robot, the more you want to spend your power and space on something else. So if you can have, again, like ants that are very responsive to the environment, even though they have very simple circuitry, then that's a kind of computer. Now, ants, of course, are not just one ant, it's a group of ants, and they also have a brain, underground. But as a general rule, I would say that very small computers, not even ant scale, even smaller ones, let's call it molecular computers.
Right?
Let's call bacterium size computers, robots, devices. Okay, when you're small enough that, let's put it this way, sub-integrated circuit size. The minute you're smaller than an integrated circuit, then it's much more difficult to put computing on it. But something really simple like the Pebble following, you can do that. That's what I think about when you ask why would we want to do it.
I was thinking about it in terms of time. Like if you were going to make a 10,000 year robot, you might want to store things in geological terms, not in digital and magnetic terms.
What about in terms of the the pattern that the robot's looking for, right? So whether the markings essentially, so it's has a camera that's, you know, looking at the spray paint on the road for the different infrastructure signals, or microphone is listening to bird songs and triangulating the birds, or a chemical, a nose that smells like ant pheromones. You know, it's like, what is the input?
I think this relates to the point we were making earlier about most of the information in the environment is like wild noise. I think you're pointing out that sometimes part of that information is in fact the information of interest that you want to compute with. So traffic signs are of course in the designed end of the spectrum, but birdsong is interesting. Like if you're designing a network of like wildlife research robots, most of the information they're dealing with is wild information that's in the environment, including, you know, sounds and sights. But related to like really long times, I guess a classic example of like extremely long period computation is the whole nuclear waste site marking thing of like, this is not a place of honor. You guys are familiar with that, right? So that's spatio-temporal computing over thousands of years, where you cannot expect that there'll be computers and communication networks, but you have to communicate a message that this is a dangerous location. Anyway, all right, so we are on the hour. So I don't know what I'm going to do with this line of thought, but I am kind of vaguely interested in maybe making, since we're talking about simulators, like maybe make a Pebble Automaton simulator as a JavaScript page, because it seems simple enough to do. And that might be an interesting starting point for something. And I think it's somehow fits into this whole tail scale type discussion we are having of like, I don't know, simpler computers connected in a network that are also robots. Anyway, so that's all I had. Any other thoughts, anybody? All right, I can stop the recording now, and that's it for this week.